So in summary, I will briefly touch upon the use of the mass transfer coefficient, or KLA, as a scale factor for scaling gas-liquid reactions. I'll talk a little about the experimental method that we use to determine KLA here in our laboratories. And I'll also discuss briefly a statistical model that we created to predict KLA in some of our reactors. I'll then relate this to a recent issue that we had observed upon scale-up of a heterogeneous hydrogenation in production. I'll then move on to talk about how we set out to develop in silico models to describe this problematic hydrogenation reaction, and how we have used those models to develop a strategy to successfully scale that reaction. And we also needed to apply some baseline correction and scaling, as in some cases we for instance started off with a slightly negative quantity of our product, which, things that aren't chemically feasible. So then the adsorbed products would desorb into the liquid phase, and that rate of desorption again being proportional to the percentage of covered active sites on the catalyst surface. So you can see the added complexity in the DynoChem process scheme here on the left. In addition to the fundamental chemical transformations listed at the bottom, we also have these adsorption-desorption equilibria reactions for each individual species. We also combined the amine and the amide into a single product species for simplicity. And as I mentioned, we removed ammonium methylvanadate from the system. Acetic acid, which was included in the system to enhance the rate of cyclization to the amide, was fixed throughout. So what I have here are some model data versus some experimental data. This is the same experimental data set in both cases. It has just been analyzed in the top graph using the first order kinetic model, and in the bottom graph using the Langmuir-Hinshelwood model. And what you can see is a greater degree of visual fit for starting material consumption, combined product formation, and hydrogen uptake. These results were kind of mirrored across many experiments. This is just one example, but the Langmuir-Hinshelwood model was giving a good fit. So I think now I'll switch to showing you what the model itself looked like within DynoChem. So what we have here, this is the process sheet. We have our phases defined, our bulk liquid phase and our headspace phase. And you can see the number of species we have in the bulk liquid phase, as this includes not only the free species, intermediates, products, starting material, catalyst, etc., but also their counterparts adsorbed onto the catalyst. The headspace contains simply hydrogen gas and an amount of THF vapor as defined by the Antoine equation. Within the bulk liquid, we have a number of experiments, a number of reactions that are occurring. We have the 5 individual adsorption-desorption equilibrium, and we have the 3 fundamental chemical steps. Next, we have the mass transfer defined between the bulk liquid and the headspace. There are 2 mass transfer processes occurring. There is the dissolution of hydrogen gas from the headspace into the bulk liquid, the extent of this dissolution being defined by the Henry constant. And then, as I mentioned, the Antoine coefficient defining the quantity of THF in the headspace. We use DynoChem to create both a kinetic model, which was then subsequently expanded into a physical model. This physical model being capable of predicting reaction temperature profiles and maximum exotherm, primarily as a function of agitation speed, but but also varying other parameters. And we believe that this approach could form the basis of a scale-up strategy, allowing you to successfully and safely scale highly exothermic reactions such as this. And at this point, I will point out that this work has been it's been written up into a paper in greater detail and submitted to OPRD, where it's currently in review.